In the last class, we calculated pHs being given the concentration of H plus and OH. In this class, we want to calculate the pHs of real substances. For example, if I ask you something like, what is the pH of 0.1 molar acetic acid? We want to be able to get that. In order to do those kinds of problems, though, we're going to do 4 different substances today. We're going to do the pH of strong acids and weak acids, and also strong bases and weak bases. In order to know what these are, I have to tell you what each of these classes are and what is in them. So the first thing on this page, you already know that an acid starts with an H in an inorganic acid. There are strong acids that ionize or dissociate 100%. Dissociate means splitting. A dissociative reaction in psychology is like schizophrenia or split personality, so that's the word they use. Hydrochloric acid, stomach acid, is one of these. If you put HCl in water, you will not have any HCl molecules. It will all be ions. Another one is nitric acid. The way I teach these is that there are actually 6 of these. You don't need to memorize the names of them, but you want to recognize the formulas, because then if you recognize the formulas of the 6 strong ones, any one that is not strong is weak. The other acids that are strong ones are well, first of all, the 3 halogens in the middle of group 7, HCl, HBr, and HI. Those are strong. The problem is that the top one, HF, is actually weak, and we're going to talk about that. Nitric acid, nitrate makes everything soluble, so it also makes a strong acid. Perchlorate, perchloric acid, loses the H very easily because those oxygens all pull electrons away from the H a lot. And sulfuric acid is actually a diprotic acid, and we're going to show that only the first H is lost 100%. The thing about that sulfuric acid is that there's 2 steps, and we have to talk about that when we do diprotic acids, but it is strong. There is a 7th one that you'll never see really in the lab because it decomposes at room temperature. HClO3 is on the borderline of being strong chloric acid, but I don't give that one because it's kind of unusual. So these are the 6 that I use. Of course, that means weak acids do not ionize 100%, and most of the time it's much less than that. They might split apart 1%, less than 5%. And there's a couple hundred of these in inorganic chemistry, and there's an infinite number of them in organic chemistry. I wanted to show you a few that you need to know a discrimination between these and the strong ones. Hydrofluoric acid, the top halogen, is actually a weak acid. Nitrous acid, HNO2, is a weak acid, but HNO3, nitric acid, is a strong one. And acetic acid vinegar is a weak one. The thing is that only one of the H's comes off. The other 3 do not. And I want to show you why that is. You don't have to know this structure, but I want to show you. A lot of the organic acids are like this. There are 3 H's that are connected to C, and carbon-hydrogen bonds are not acidic in organic. Only the H that's attached to the oxygen actually comes off. And so the 3 in the middle of the formula do not ionize. You have a table of weak acids that have a value called Ka, which we're going to look at later. And these acids all lose 1 H plus on page 9. The only thing I want to look at about these right now is that you don't have to know all these names because they're right in the table. But this is what you use for acid problems. There's also a fourth column that's called pKa that we're not going to use today, but we will use when we do buffers, but you already know what that is because a lowercase p means it's the negative base 10 log of the Ka. On the back of that page in table 2, there are acids that are called polyprotic. They give off more than one proton, or H. And these are either diprotic if there's 2 H's or triprotic if there's 3. The only thing I want you to pay attention to at this point is if you look, for example, at the top acid, carbonic acid, it does not lose both of the H's together. It loses them in steps, one at a time. And each of the 2 steps has its own Ka. Those are called Ka1 and Ka2. And of course, each one has a pKa. There's even a triprotic acid in the middle called phosphoric acid that loses 3 H's. First question I want to ask is, how would a chemist know whether an acid is weak or strong? When you're studying it, there's all kinds of ways to do this, but I want to show you one way. In chemistry, you can use a device that's called a pH meter. It's very simple. It's got a digital display on it. It can be attached to the electrode, or you can attach it by a wire to a box with the electronics in it. There's an electrode that has a glass bulb at the end that's sensitive to H+. And you can use it if you calibrate the machine correctly. You can stick the electrode in any solution and the pH will read out. And so if you make, for example, a solution that is 0.1 molar in HCl, the pH you measure will be about 1. But if you use the exact same concentration of HF, your pH is going to be 3. The question is, why are they different? Well, HCl is a strong acid and HF is a weak acid. Strong acids give you more H pluses, so the pH, more H pluses makes the pH go down. So the strong acid has a lower pH than the weak one, even at the same concentration. I explained this in that list underneath the pHs. HCl makes more ions. Now, because of the fact that the weak acids are equilibrium reactions, you can write an equilibrium constant for them. The equilibrium constant is called the acid dissociation constant, which they substitute for the EQ and A. So these are Kas for obvious reasons. I'm going to use nitrous acid as my example. You follow the same rules for writing an equilibrium constant as we did in lecture 1. It's the products over reactants, and you put square brackets around for molar. Now the thing is that these are different though from KSPs that we did last class, because what's on the left in a KSP is actually a solid, and solids don't go in the expression. But I made the HNO2 aqueous, and the reason for that is that the only way for an ionic solid to dissolve is to make ions. So the solid's not involved in the equilibrium. The only thing that's in there is the ions. But in the case of an acid, that is not true. Acids dissolve 100% in water. The only question is how much splits apart. And so since the acid is dissolved also, you have to use it as aqueous, and you have to put it on the bottom of the fraction. If you look at the table again on pages 9 and 10, it has Ka values listed. If you look at the numbers, they're all very small, just like the KSP values, because what are we measuring this time? You're measuring the number of ions in solution for a weak acid which doesn't have many ions. But there's a difference because the range is not as large. You can find Ka values that are 10 to the minus 12 for hydrogen peroxide on this page. There's even one on page 10 for the last step of phosphoric that's 10 to the minus 13, but you'll never get a Ka value in water that is less than 1 times 10 to the minus 14. That's the Kw for water, and you can't measure the Ka very well for an acid that's weaker than water because it doesn't give you enough H pluses. If you look at the second step for hydrogen sulfide, HS minus is actually weaker than water. So nobody really knows the value because it's very small. Now in organic, you will be able to get Ka values for acids that are much weaker than these. But the way they do that is they measure the Kas in organic solvents, not water. And when you do that, you can get Ka values much lower. I don't think this will surprise anybody. The larger the Ka, the stronger the acid, because the larger the number means more ions, and so that's a stronger acid. So you can rank all of the ones in the table by strength. There's a problem with the terminology here, though, because the word strong is used for anything in chemistry that ionizes 100%, so strong acids. But even though weak acids ionize less than that, you can still call some weak acids stronger than others, which means they have more ions. So you can use the comparative, but you can only call strong acids those 6 I showed you. And for the same reason as in KSP, there is no KSP for a soluble salt. There's also no Ka for a strong acid. If you put HCl in water and you get 100% ions, there are no HCl molecules. So again, you would have to divide by 0, and that's not allowed. So that means Kas for strong acids are undefined, and that also means that all of the acids in your table are weak ones, except for that one sulfuric acid, which we're going to talk about individually. The first step is strong. If you look at the back page, page 10, these are the di- and triprotic acids, and we have several things that we need to say about those. I'm going to use the top one on this page, carbonic acid, and H2CO3 actually splits apart in steps. And the thing about carbonic acid is you lose one H at a time. Where does it come from? Well, it comes actually from the dissolving of CO2 in water. And I want to show that on the next slide. If you just count the atoms in CO2 and H2O, if you put them together 1 to 1, you would get a compound that has 2 H's, a C, and 3 O's. I don't want to show you the structure, but that is what you get. That's the reason why tap water is not neutral, but it's acidic, because CO2 dissolves in it from the air. H2CO3 is actually the form in your blood that you carry CO2 back to your lungs to breathe it out. And H2CO3 is also the main buffer in your blood. So carbonic acid is very important in physiology. I made those 2 steps bigger on this page so we can see them. I want to talk about what happens when carbonic acid does split apart. If you look at the first step, you lose, first of all, 1 H+, which means you're left with an ion that still has an H attached. And you should recognize that as bicarbonate ion. It's got a negative charge because if you take an H off plus, you have to be left with a negative. So when you put them back together, they're neutral. And you can see that that step has a Ka value called Ka1. If you lose the second H+ in the second step, you end up with an ion that's -2. And that's because you add +1 - 2, it has to go back to what's on the left, which is -1 again. And this one has a different Ka, Ka2. If you look at those 2 Kas, the top one is stronger by a lot, 10 to the 4th, than the bottom one is. that is true in all di and triprotic acids. They get weaker as you go down. And that kind of makes sense because when you pull off the first H plus, you can see that you're pulling it away from a -1 ion. When you pull off the second H plus, you're pulling it away from a -2. Well, pretty obviously a -2 is going to hang on to a positive better than a -1, so it gets harder to pull off as you go down. This is true in all of the acids. The next one I want to show, though, is sulfuric acid. When you lose the first H from sulfuric acid, you do end up with an ion HSO4-, but that is a strong step. It happens 100%. But then when you lose the second H from HSO4, that is a weak step, which has a Ka2. And so we're always going to have to talk about sulfate and sulfuric acid separately because it has unique properties because of that. In phosphoric acid, if you look, you lose an H plus in the first step, and you end up with an ion that still has two H's attached. And since you took off a positive, that ion is -1. And then the H2PO4 can lose an H to give you HPO4, which is -2, and then you lose the third one that gives you the bare phosphate. Now the thing is, every time you go down 1 in the ions, the charge goes down 1 because you've taken off a positive. Now this is, and the 3 Kas that you see do get weaker as you go down, which is expected. A lot of people do not understand the significance of those H's that are still attached to the phosphate. We talked, for example, in your cell, there is no H3PO4 or PO4 3-. They cannot exist at the pH of your cells. All of the ions in your cell are HPO4 and H2PO4. Phosphorylation is very important in biology, as you know. That's how you make ATP molecules. That's how you regulate enzymes, a lot of them, by phosphorylation. That's what the backbone of DNA is. And a lot of times enzymes will recognize the H2PO4 or the HPO4, and it will control what direction the reaction goes in. It can control the acidity that is produced. You got to realize the fact that in buffers, the pHs of these are completely different. You have to put this in your mental program that whether the H's are attached or not is very significant in chemistry, and we're going to talk more about it as we go. There are other triprotic acids, but I chose the one that's inorganic because we're doing inorganic chemistry, but there's lots of them in organic. The ions that come from the di and triprotic acid still have H's attached to them, and chemists have a way of naming those. If you look at any of these acids, you have things like HCO3, HC2O4-, HPO4 2-, the one that still has the H's attached. If the ion with the H in front comes from a diprotic acid, chemists just put the prefix bi in front of the name of the ion. So HCO3 bicarbonate, HSO4 bisulfate, and HSO3 bisulfite. The IUPAC name is hydrogen carbonate, but I usually see it as bi because people don't usually use those IUPAC names. Bicarbonate, as you know, is very important. You can use it, it's the main buffer in your blood. HSO4- is how you isolate aldehydes and ketones in organics, so you're going to see that again. And HSO3 is the developer for X-ray film. It turns it black. So these are used a lot. The two ions that come from phosphoric acid have their own names. You can't call HPO4 biphosphate because it doesn't come from a diprotic acid and it would be ambiguous. They just call H2PO4 dihydrogen phosphate and HPO4 monohydrogen phosphate. If you were going to write formulas with these, suppose I ask you to write the formula of barium dihydrogen phosphate. You would do it exactly by crossing, just like you do any other ionic compound. You would put barium 2 plus first, and you have to know that H2PO4 is -1. The way I remember it is, you know PO4 is -3, so if you add 2 H pluses, you get a -1. And then you cross, and those ions look just like a regular ionic compound. Here's another example of a compound with a very long name, but that's okay. It's a good example. Ammonium monohydrogen phosphate. The ammonium is the NH4 plus. HPO4 2 minus is monohydrogen phosphate. So when you cross, you end up with the formula shown, and there's really nothing you can do with it. This isn't that critical a thing, but I did want to show it to you because you will definitely run across these names somewhere in your career in the future. This is the problem that we really want to get to today. The question says, what is the pH of 0.0079 molar HClO4? Within the next 4 lectures, we are going to have 7 different substances that you can fill in for the question, what is the pH of? And each one of them has a different problem to do. If you can't figure out what the substance is, you will do the wrong problem and get the wrong answer. So the important thing, first of all, is being able to classify these substances. I'm going to do a lot about classifying them. We are going to do strong and weak acids, strong and weak bases, and diprotic acids. And then in later classes, we're going to do salts and buffers. We're going to calculate the pH of all of those. This one is a strong acid because HClO4 is one of the 6. So let's see what happens. HClO4 is going to ionize 100%, which means that if you start with it unionized, after it splits apart, there's not going to be any of the molecules left. And as we talked about last class, when you split apart 1 to 1, the 2 ions are going to be exactly the same concentration as what you started with. We don't really care about the ClO4 because that's not going to affect the pH. What we care about is the H+. In order to get the pH from the H+, it's minus the log. And if you take minus the log, you get a pH 2.1, which is appropriate because it has to be below 7. This is an acid. I'm giving you a rule for this. I don't really like these because a lot of times what people do, this is the easiest one, and what they'll do is they'll only learn this one and apply it to all 7 problems, and then you get 6 out of 7 of them wrong. But for H+ in a strong acid, this is true that the pH just equals minus the log of what you're given. And I don't have to ask you for the percent ionization because you know, since it's strong, it's 100%. But if you're going to do a problem with a weak acid, it's going to be different. I'm going to ask you for the pH and percent ionization of the same concentration of acetic acid. And acetic acid is a weak acid because it's not one of the 6, and it's also in your table. Since the acid is weak, we don't know how much of it is going to split apart. And so you need to introduce an X into the problem. Whenever you introduce an X in an equilibrium problem, that's when you have to make an ice table. So I'm starting with the initial concentration of 0.0079, and next we need to do the changes. And you already know that you're going to shift towards the zeros. So the pluses always go on the side with the zeros and negative on the other side. And the concentration at the end is what you started with and what you changed. So you end up with 0.0079 minus X for acetic acid. In order to get the pH, we have to solve for H+, but the H+ in this problem, the way it's defined, is actually X. So what we need to solve for is X in order to get the pH. The only number we have is the Ka, which you could look up on the table. So I wrote the expression for Ka, products over reactants, and then you can plug in the last row of the table. So I plugged in X for each of the products and 0.0079X for the reactant. And of course, X times X is X squared. You can look up the Ka value for acetic acid in table 2. And so it's 1.8 times 10 to the minus 5. That's what you set it equal to. So the idea is that after you plug it in, now we have to solve that equation for x. And now we can all cry together, because when you have x squared and x in the same equation, that's a quadratic. The question is, are you going to have to use the quadratic formula and do all that ax squared plus bx plus c equals 0 business? Well, the answer is no. I like to call myself the master of simplification. I've got about the simplest mind on earth, and I like to do things easily, so we're going to be able to get away without that. A lot of times in math, if you are subtracting or adding a very, very small number relative to a very big number, you can ignore what you're subtracting. Let's suppose that I gave you $10,000 and told you, oops, I got to take $1 back because you had to enter the contest. You're not going to really get that shook about it. Or if I gave you an extra dollar afterwards, so you got 10,001, it's not that big a deal. So in other words, a lot of times you can just ignore a small number relative to a big one, and it won't really change the answer that much. We're going to show that you are allowed to do that in acid problems, because how big is x compared to the 0.0079? Actually, it's very small, probably 1%, because x is the amount that splits apart, and we already said that weak acids only split apart about 1%. So x is going to be small relative to the starting concentration. If you take out that x, if you did that in math class, your math teacher would absolutely crucify you. But in chemistry, we're talking about experimental error. It's not going to change the answer that much, and I'm going to prove that to you. If you take the x out, the equation you're left with is much easier to solve. All you have to do is multiply both sides by 0.0079, cancel it, and then take the square root. And that gives you the H plus. And if you take minus the log, you get the pH. And this is a good pH also for an acid because it's below 7. I wanted to show you, though, that if you do use the quadratic formula, you're not going to get that much different of a number. So I did that, and I took x squared over 0.0079 minus x equals the Ka, and solved it for x. How would you do it that way? You would have to multiply both sides by 0.0079 minus x, and then distribute the 1.8 times 10 to the minus 5 over both of them. And then you'd have to rearrange it into the form ax squared plus bx plus c equals 0 and plug into the quadratic equation. When I did that, I got an answer for x that was 3.68 times 10 to the minus 4, which is a little bit different than the x we got when we took out the x relative to the original, but it doesn't look like that overly much. And when you take minus the log, look at what the difference in the pHs is. 3.43 and 3.42. You can't even measure that accurately on a pH meter. So I'm going to tell you that in our class, you'll always be able to ignore the x relative to the starting concentration. I'm going to talk a little bit about when you would maybe not be able to do that, but in this class we're going to do it because it hardly ever changes the answer much. I want to concentrate on the important thing, and that is we did both acids, a strong one and a weak one, at the same concentration. The pH we got for the strong acid was 2.1, but the pH we got for the weak one was 3.42. Now, even though they're both the same strength, why are they different? Because the strong one gives you more H pluses, and it makes the pH go down. So this is appropriate, and it's consistent with what we know about pH. In the case of the strong acid, we didn't have to calculate percent ionization because you know that it is 100%. But in the case of a weak acid, they're all different. And so you need also to calculate what percent of that acid ionized. I know that everybody knows how to do percentages. If I gave you a problem like what percent of 300 is 7, everybody would be able to get it on the calculator by messing around with it. The thing is that when you're asked a percentage problem on something like this, what in the world are you going to use to get a percent? There's all these numbers and x's and everything else. Well, I'm going to show you a formula, and I can tell you that you can use this in physics and biology in any field that you want. A lot of people have seen this formula, that a part over a whole times 100% is how you get a percent for a problem like this. I don't know how many people actually understand how to use the formula, so I want to show it to you. Why is this 100%? Why does this give you a percent? I just drew a circle as an example. If you have 4 parts and you only color in 1 part, you know that that's 25% of the circle, but why? One way to calculate it is just to say you have 1 part, put that on the top. If you have 4 parts, which is the whole, you put that on the bottom, times 100% gives you 25%. So when you're doing a problem like an acid problem, you have to figure out, what am I going to use for the part and what am I going to use for the whole? So if you look at this ice table, what would you think you would use for the whole? Well, you're going to use the original amount, 0.0079. And you want to know what percent of that formed ions. Well, the reason why there's a minus x in the change row is that the original amount split apart a little bit, and the x is the number of molecules that actually formed ions. So if you want to get the percent ionization, you can take what we got for the x, or the H plus, which was the number on top, divided by the original amount times 100. And 4.8% is the amount that actually formed ions. The formula is always x divided by the original. In a base problem, the x will be OH, but it doesn't matter. It's always what you get for x on the top. Chemists have a kind of rule of thumb. It's called the 5% rule, but I've shown myself that this doesn't really work exactly. It depends on both the concentration of the acid and also the Ka. But the old thing they did was they said if the acid ionizes less than 5%, you can ignore the X relative to the original concentration, because then the X would be very small. The thing is that I've done problems where you do 6%, 8%, whatever. It still doesn't change it very much. The only thing I've ever found where you have to worry about doing the quadratic equation is actually for sulfuric acid, because the second step of sulfuric acid is pretty strong, even though it's a weak acid. And so sometimes you get both of the H's coming off, and sometimes the first one comes off and only part of the second one. That's when you have to worry. But I just decided I don't want to do sulfuric acid problems. They're complicated and they're not really that important. So we will always be able to ignore the X. This problem is asking to calculate the pH of another weak acid, but this one is a diprotic acid. We want the pH in percent ionization of 0.1 molar carbonic acid. And of course, that's the acid that we looked at earlier. It's the top one on page 10, and it's got 2 steps. You might think this would be a really tough problem because you now have H plus coming from 2 different places. Do you have to calculate the amount you get from step 1 and then the amount you get from step 2 and add them? Or what if they affect each other? One suppresses the other. What is the complication here? The truth of it is you can do this very simply. Remember the master of simplification. The second step is much, much weaker than the first step. So the question I want to ask first is, how many times stronger is the first step than the second? If you take the top step minus the bottom and use the property of exponents, you find out that the top one is 10 to the fourth or 10,000 times stronger than the second step. If you translate that into English, what it actually means is that for every 10,000 H's that you get from step 1, you're only going to get 1 from step 2. That means that you can just ignore the contribution of step 2 because it's not enough H's to change the pH significantly. So the rule I want you to remember is that when you're calculating the pH of a diprotic acid, you just forget that the second step is even there. You only use the first step and you do an ordinary weak acid problem like we just did with acetic acid. And if you look at that ICE table, it's exactly the same as acetic acid, except we're starting with 0.1. And when you set up the Ka, you're still going to get x squared divided by the original. You have to set it equal, though, to the first step of carbonic acid, because that's the step we're using to calculate. And then you can ignore the x relative to 0.1 and solve the equation you get. So if you solve that equation, multiply both sides by the denominator, take the square root, the x gives you the H plus concentration, and to get the pH, you just take minus the log. And 3.69 is a good pH. It's below 7 for an acid. If you want to get the percent ionization, you use exactly the same formula. You take whatever you got for x, put it on the top, whatever the original was, 0.1 on the bottom, and you multiply by 100. The thing is, this percentage is more like what weak acids are usually like. The previous problem was 4.8% ionized. That's very unusual. Usually weak acids are down around 1% or even less. So when you're presented with a problem where you have to calculate the pH of a diprotic acid, all you have to know is that you only use step 1 and you ignore the second step. Otherwise, it's the same as any other weak acid problem. We've calculated the pH of strong and weak acids. Now we want to calculate the pH of strong bases. What is a strong base? First of all, it is a metal ion, which is positive, combined with the negative ion OH, because OH makes everything a base. So these are ionic compounds, and we're going to only calculate the pHs of the strong ones by the method I'm going to show you, but it works. Actually, solubility rule 3 says that most of these are insoluble. There's only a few that dissolve. So I'm only going to give you problems with the soluble ones, but any of the metals from rule 1, that means group 1, will give you a soluble base, and then also strontium and barium hydroxide. Those are also soluble. I gave you some examples here of typical ones. A metal that combines with OH and makes it soluble. That's what we're going to do problems about. Now in this problem, I used the same concentration as I did for 2 of the acids, 0.0079 molar, but the question is, what is the pH of sodium hydroxide? This is the place where I want to show you that sometimes I don't give you the molarity directly. Sometimes in these problems I have you calculate it. So I could give this problem as, what is the pH if you dissolve 1.17 grams of sodium hydroxide in 3,700 ml? The only difference between this problem and the one with the grams given is that you have to take those numbers and calculate the molarity yourself first. And then after that, you do the problem exactly the same way. Most of the time, I'll give you the molarity, but I have to give you 1 or 2 where you have to convert to molarity, and so then do the problem after that. Now, because sodium hydroxide is strong, it's going to split apart 100%. So the question is, how much is going to be left after it dissolves? And of course, just like anything strong, you're going to have none of the sodium hydroxide units left at the end, and the ions are going to have the same concentration as what you started with because they split apart 1 to 1. When we were doing the strong acid problem, what you did was you took minus the log then of what you were given. You're still going to do that, but the difference is this time that is not the pH, because the 0.0079 this time is OH. So we have to calculate that OH and convert it to pH. So what the minus the log gives you is actually the POH, and then we convert it to pH. You take 14 minus the POH, and you get the pH. This is a good pH for a base. It's above 7. Now you have to know that when you're doing a strong base, then there's one extra step over and above a strong acid. You take minus the log, but then you also have to remember to do the 14 minus step at the end in order to convert it back to pH. If you came out with 2.1 as the answer for the pH of a base, I just want you to think before you put that number down, because you know a base has to have a pH above 7. You can't possibly be below, so you know something's wrong. That should help remind you to do the subtraction. Now I want to calculate the pH of the same concentration of barium hydroxide. You would think it might be the same thing because barium hydroxide is also a strong base, but you really have to watch it, because if barium hydroxide dissolves in water, you actually get 2 OHs for every 1 barium hydroxide. That's the reason why after dissolving, you are actually going to end up with 2 times the original amount of OH. It's a very typical error of students not to do the multiplying, but if you understand dissolving, you can see why you would have to multiply the original amount by 2. Then, because it's OH, you have to do that same step where you do 14 minus. So when you take minus the log, you have to take 14 minus it to get the pH. The last problem was 11.9, and this problem was 12.2. It doesn't look like that much more pH, does it? The question is, why couldn't I get the pH in this one by just multiplying by 2? I mean, after all, there's 2 times as much OH. So why couldn't I just take the pH from the previous problem, 11.9, and multiply it by 2 and gives you a pH of 23.8. Well, you can't do that because pH is a log, and logs do not work the way normal numbers do. We talked about the fact that the exponent in the equation 10 to the power is actually the log. So actually the concentrations of H plus or OH are acting like the anti-log, but the pH and the POH actually act like the exponent. So you have to look at how the exponent changes when you're doing pH, not how the H plus and OH concentrations do. I want to give you a problem here where we're going to come up with a rule of thumb where you don't even have to calculate a lot of times. You can do it in your head. And I really want you to know this principle, so I'm going to tell you, we're going to start with a concentration of H plus in solution so that it's 1.0 times 10 to the minus 6 molar. What is the pH? You can do this one in your head. I mean, if you realize the fact that pH is the exponent and the 1 is just 1, minus the log of 10 to the negative 6, this is 6. And you can get that and just calculate it in your head. Of course, if you do it on your calculator, you'll still get 6, but it's nice to do things in your head too. So what you're doing is you're starting with a solution at pH 6 that has that concentration of H plus. Now the problem says, what happens if you add enough acid so that the H plus goes up to 1 times 10 to the minus 4? What is the new pH? Well, it's the exponent again, so the pH goes to 4. What we're going to ask here is, when you add that H plus and the pH changes by what they call 2 units, because when you go from 6 to 4, they call that changing by 2 pH units. But what I want to ask is, how many times more H plus did you actually put into the solution? If you take the 10 to the minus 4 that you got after divided by 10 to the minus 6, it shows that you put in 100 times more acid. And of course, 100 times more is 10 squared. So look at what happened. When you change the concentration by H plus by 10 squared times, how much did the pH change? It changed 2 units. The pH changes like the exponent and not like the concentration. And you can do this in your head if you know how many pH units you changed. I want to put this in the form of a rule that we can test. So in that problem, we said that when the concentration of H plus changed by 100 or 10 squared, the pH changed by 2 units. You can say that in general by saying that when the pH changes x units, the H plus or the OH changed 10 to the x times. If you plug in the 2 for the pH units change, you can plug in the 2 for 10 to the x. So when it changes 2 units, you change 10 squared times. I want to show you that this even works for decimals. When we did the 2 problems with sodium and barium hydroxide, sodium gave a pH of 11.9. Barium hydroxide went up, but not much. So I want to ask, how many pH units first did this change? If you subtract the numbers, you find out that the pH went up by 0.3 unit. If you put that into the rule, when the pH changes 0.3 units, how much do you expect the H plus or OH to change? You expect it to change 10 to the 0.3 power times. Can you even do that? I mean, is it possible to raise 10 to a decimal power? Well, in math, you can do that. As I underlined at the top there, if you take 10 caret 0.3 on your calculator, you will get 1.99999, which is 2. So in other words, even for decimals, the principle works. I put those into the rule, and you can see that when the pH changes 0.3, the H plus changes 10 to the 0.3, which is 2 times, and that's exactly what we said. I know I put problems like this on the test because they're very helpful to be able to do in your head, so let me show you one. Let's suppose that you start with a pH 5 solution and you add enough H plus to it so that the concentration of H plus gets 1,000 times greater. What is the new pH? So here you are, you're starting with 5 pH, and you add 1,000 times or 10 cubed more H plus. Now, you might be tempted to say 8. That's wrong. You might be tempted to say 3. That doesn't make any sense. What would the new pH be? Well, first of all, the pH is going to change by 3 units because it's 10 cubed. And because you're adding H plus, the pH is going to go down. So if you go down 3 from 5, you're going to get a pH of 2. So here it is. When you change by 10 to the third, you change the pH by 3, so you went from 5 to 2. So back to where we are, we have done strong and weak acids and strong bases. The last thing we have to calculate the pH of is actually weak bases. And weak bases are different because they do not have OH in the formula. There's obviously something different about weak bases, because I'm going to tell you this first. F minus is a weak base. But if you look at it, you say, why would that be a base? It doesn't contain OH, but you still call it a base. Another one that might even be more mysterious is NH3, ammonia. Why in the world would that be a base? It doesn't have OH, and it also has 3 H's in it, so you would think maybe it would be an acid that would give up an H+. But I'm going to tell you that these are definitely both weak bases. What a weak base does, and why it's called that, is that these are substances that do not have OH in the formula, but when you put them in water, they react with water to produce OH. How did they do that? Well, if you put one of these bases next to a water molecule, it pulls an H off the water, and if you pull an H off a water molecule, you end up with OH minus. And so they act as bases when you put them in water. There are two different kinds. Ammonia, for example, is a neutral molecule, and fluoride is an anion or a negative ion. We're going to discuss ammonia first. This is what ammonia does when you put it in water. This reaction is equilibrium. It only occurs about 2%, but it does produce enough OH to make a very basic solution. What happens is the NH3 pulls the H off of water, and when it does that, you form the ion NH4+, or ammonium. When you take the H off of water, you form the ion OH-, which makes it a base. The reason why NH3 is not an acid in water is that if you try to take an H+ off, you can get this ion called amide, but the truth of it is NH2- is so reactive, you can't put it anywhere near water because it'll react so violently. You can use that in organic chemistry, but they use it in liquid ammonia, not in water. I'm showing here by Lewis structures what happens. We're not going to draw Lewis structures in this class, but boy, when you get to organic, you're going to draw all kinds of them all semester. But I want to show you what actually happens here. Ammonia is 5 electrons in the valence shell, so it has 3 singles that pair with the hydrogens and 1 unshared pair. Water has got 2 unshared pairs on the oxygen. But what happens is when you put ammonia next to water, the H moves from the water molecule and bonds to the unshared pair on the nitrogen. This is what's called one of those coordinate covalent bonds, where both of the electrons come from the same atom. And so you end up with a positive across the whole molecule, which is called ammonium, NH4+. And when you take the H off the water, the electrons that were in the bond stay behind on the oxygen, and you end up with OH. And this is equilibrium. Ammonia dissolved in water has all kinds of names. They call anything dissolved in water something water, like ammonia water, chlorine water, bromine water, but that doesn't tell you too much about it. I don't like the name ammonium hydroxide, which is what they call it if you buy it from a chemical company, but that's really a bad name because ammonium hydroxide does not even exist. If you try to put ammonium with a hydroxide, all that's going to happen is the OH is going to pull an H off the ammonium and give you ammonia and water. The only place where you see ammonium and hydroxide together is in solution, and at that time it's only about 2%. I call NH3 aqueous exactly what it is. NH3 aqueous. It's aqueous ammonia. It's ammonia dissolved in water, and that is what the solution actually is. Because of the fact that ammonia reacts with water in equilibrium, you can write from that equation what's called Kb. And again, you put the products over the reactant, NH3. Liquid water does not go in the K. And this has got OH in the top, so the base dissociation constant, Kb, has OH in the top. Now the thing is, for doing problems where we calculate the pH of a weak base, you need to get values for Kb. And you can find tables that have these in them, but they usually only put in neutral ones like ammonia, and there's a whole bunch of neutral ones in organic chemistry. But the only one we would put in a neutral table was NH3, because most of our weak bases are actually negative ions. So what I want to do is, I don't want to give you a table of Kb's. I am going to show you that it's possible to calculate Kb from the Ka of the corresponding acid. So we're going to use the same table, the Ka table, to get Kb's as well, but you have to calculate it. And in order to do that, we have to talk about the Bronsted theory of acids and bases in order to show how that works. The Bronsted theory is the second theory of acids and bases that was proposed. The one that's usually used, that's H plus is an acid, OH is the only base, and when they combine they make water. That is called the Arrhenius theory, and it's very useful. It was proposed around 1900. The thing is, it doesn't really explain buffers very well, and it doesn't explain other aspects of acids and bases completely. So in 1945, the year World War II ended, the Bronsted theory was proposed. It does several different things, but one thing it does is it explains buffers much better. And secondly, it increases by a lot the number of bases that can be classified that way, because it gives you a huge number of bases that can react with water. So here's the basis of the Bronsted theory. It takes advantage of the fact that we know that hydrogen ions never exist free in water. They always have to be attached to something. In pure water, if you put H plus in, it's going to attach to water molecules. And this is what we called hydronium ion, or H3O plus. But even if it's not bonded to water, it can't be free. It still has to be attached to something else. So Bronsted theory looks at the H plus as not being released. It looks at it as being donated to another substance. So when you start with a Bronsted acid, they define it as a substance that donates H plus or a proton to another substance. Most of the acids that are Arrhenius acids, well, all of them are also Bronsted acids because they donate H plus. The thing is that makes the definition of a base pretty obvious, that it's the substance that accepts the H plus from the other substance. So Bronsted theory never allows H plus to be free. It's always going to be, some people are going to argue over it. Two ions are, or a molecule and an ion, and the H is just going to get transferred from one to the other. The reason why that Bronsted theory is so useful, one reason is that there's way more bases in the Bronsted theory than just plain OH by itself. In the Arrhenius theory, OH is really the only one, but in Bronsted theory, you can have negative ions like F minus, as we showed in that slide before. So in this case, I'm going to write HF the way we've been showing it, dissociating into H plus and F minus. But because we know about H3O plus, what this actually does is that HF actually donates the H plus to a water molecule. When it does that in the forward direction, you form H3O plus, and you also get the ion free. If you look at the reaction going in the reverse direction, it's actually the H3O plus that's donating the H to the F minus. And so this is how a Bronsted reaction always works. There's always an acid and a base on each side of the reaction. In this case, when you're going in the forward direction, it's the HF that's donating the H, and so HF is the acid. Water is accepting the H plus, and so it's a base. You could never call water a base in the Arrhenius theory because a base is OH, but water can be a base if it accepts an H plus. And as we said, if you're going in the reverse direction, you would have to call H3O plus the acid, because it's donating the H, and you would have to call F minus the base because it is accepting an H. The problem comes in when books try to explain the word conjugate. using these kind of equations. And they are very confusing usually. I want to explain the word conjugate the way chemists usually use it, because it's very common in buffers and bases. So the way Bronsted theory works is that if you have an acid like HF, as soon as the HF gives up the H+, it immediately becomes a base. The F- is a base, because after it loses the H, the F- can take the H back. The way the Bronsted theory uses this is that they call HF and F- a conjugate acid-base pair, because conjugate means it goes together. HF would be called the conjugate acid of F-, and F- is called the conjugate base of HF. And you could do the same thing with H2O and H3O plus. If you look at this, HF and F- are conjugate acid-base pairs, so are H3O plus and water. H3O plus would be called the conjugate acid of H2O, and H2O would be called the conjugate base of H3O plus. All conjugate acid-base pairs differ by one H plus. And you have to restrict it to just one because of buffers. It sounds kind of picky, but right now we have to restrict it to one. And so I'm going to say they differ by one H plus. And here's another thing that results from that definition of conjugate acid-base pair. Let's suppose you start with an acid like HA, and I ask you, how do you make a conjugate base out of an acid? So you say, what is the conjugate base of HA? Well, if you take the H off of the HA, the A- that results is now a base. And so they call it the conjugate base. If you take a base like A- and you stick an H onto it so that it now turns into HA, that's an acid, that's the conjugate acid. So what we're saying is that if you lose an H from an acid, you form the conjugate base. If you gain an H on a base, you produce the conjugate acid. So here I wrote that. Anytime you take an H off an acid, you get the conjugate base. Anytime you put an H on a base, you get the conjugate acid. And as I said before, in order to be a conjugate acid-base pair, they can only differ by one H. And that's because of buffers, and we'll see that later. So just to reinforce this, I want to ask you a couple of questions about these. Let's say that I said, what is the conjugate base of HCN? Well, HCN is an acid, so if you want to get the base, you take off the H. And it's Cn minus because when you take an H off, you get a negative ion. Second one says, what is the conjugate acid of ClO minus? Well, you're going to stick the H on. And because you added a positive, the S is neutral. The third one says, what is the conjugate acid of CO3 minus? This one you have to be careful of because you could have two choices, but you really don't. I'm pointing to CO3 minus. If you put one H on, you get HCO3. But if you put both H's on, you get H2CO3. They can only differ by one H to be a conjugate. And so the conjugate is actually HCO3 minus. The next one says the conjugate base of H2PO4 minus. Well, in that one, you're only going to remove one H. So the conjugate base is HPO4 2 minus. Now what we're wanting to do is calculate the pH of a weak base. The thing is, it's very important to understand that a weak acid looks a lot like the weak base, but they are completely different substances. And I want to show you that in the next slide. HF and F- don't look very different if you're not familiar with the chemistry principles, but they are extremely different. If you dissolve HF in water, it is an acid. you're going to get an acidic solution. But if you dissolve F- in water, it is actually a base, and you cannot get much more different than an acid and a base. I'm pointing to HF because it's an acid, and everything on the left of the arrows in the Ka table is an acid. If you remove the H, you get F-, which is the conjugate base. So that means that in this Ka table, everything on the left of the arrows is an acid, and everything on the right is the conjugate base. And the other thing I want to make sure you understand is that since the acid HF is weak, that means that it doesn't lose the H plus completely. So that means when you look at the F- on the other side, it's going to also be a weak base because it doesn't accept the H back completely. It's an equilibrium. There's only one truly strong base in water, and we're going to see that the only one that's really strong in water is OH, because you can't get any stronger than that in water. At the top of this page, I showed the dissociation equation for HF. And that equation has got a Ka associated with it. The thing you have to figure out is that we know what the Ka value is from table 2. You can look it up. But we also know that if you dissolve F- in water, which is what we just looked at in that in the second beaker in the page, that it will give you a basic solution because F- is reacting with water to pull off an H. The reaction that we want for the Kb is not the reverse of the Ka. The reverse of the Ka is when you put F- into an acid. What we want to do is put F- into pure water. And so that's what I'm showing at the bottom of the page. And if you write the Kb for the F-, that's the number that we don't know. And we need to calculate because it's not in the table. We can do that if you multiply two numbers together, which I'm just going to do it randomly just to see what happens. You have to just hang in there a minute and you'll see why in a second. But I'm going to multiply the Ka of HF by the Kb of F-. If I do that, you can see that there's canceling that can be done. The HF cancels and so does the F-, and what you're left with is H plus times OH, and I know what that number is. That's 1 times 10 to the minus 14, or the Kw for water. So what we just derived is that if you take the Ka of an acid times the Kb of the conjugate base, you will get 1 times 10 to the minus 14, which means that Ka and Kb have the same relationship as H plus and OH. If you take 1 times 10 to the minus 14 divided by one of them, you get the other. The first problem I want to do then is to calculate the Kb of F-. If you look at the Ka table, you can see where HF is, but the number 7.1 times 10 to the minus 4, that's the number that corresponds to the Ka for HF. What we want to get is the Kb of the F-, which is the conjugate base, on the other side of the equilibrium. That's the K for the reaction of F- with water to make OH. The way you do this is, since we know what the Ka is, all you have to do to get the Kb of F- is to take 1 times 10 to the minus 14 divided by the Ka, and there it is. Now we want to calculate the Kb of ammonia. That's the reaction where you put ammonia in water and it pulls an H off of the water molecule. The row in the Ka table where ammonia is you can see that it's on the right of the arrows, which means it is a weak base. Ammonium is on the left of the arrows, NH4+, and that is a weak acid. So ammonium and ammonia are two completely different substances. One is an acid and one's a base. And the number in the table that you see for Ka corresponds to NH4+. We want to use that to get the Kb for ammonia. So we're going to take 1 times 10 to the minus 14 divided by the Ka, and that gives you the Kb. Now I want to calculate the Kb of carbonate, CO3 2-. And this one can be a problem because you're only supposed to add 1 H+, if you remember. The place where CO3 is on the right of the arrows, so it's a base, but you notice that it's in the second step for the carbonic acid. So when you do the, when you get the Kb, you want to use the Ka2, not the Ka1, because carbonate is in the second step. Since carbonate is in the second equation, the 4.8 times 10 to the minus 11 is the Ka for bicarbonate that we're going to use to get the Kb for carbonate. This is the equation for carbonate pulling off 1 H from water and becoming bicarbonate. This is what we want the Kb for. So when you take 1 times 10 to the minus 14 divided by the Ka, you get the Kb. And I don't think it's going to surprise anybody that the larger the Kb, the stronger the base, because we've already had several of these. The larger the Ksp, the more soluble the salt. The larger the Ka, the stronger the acid, and the larger the Kb, the stronger the base. So you can rank the bases that we just did in order of their strength. If you can remember this concept, you'll be in good shape for the rest of this class. That everything on the left of the arrows in the Ka table is an acid. Everything on the right is the weak base. The Ka value in the table is for the acid on the left. In order to get the Kb for the negative ion or ammonia on the right, you have to take 1 times 10 to the minus 14 divided by the Ka. This skill, though, is the absolutely most important one to get these problems correct. I'm not going to tell you what kind of a substance it is or what kind of problem to do when I give you a problem. So you have to be able to classify this stuff as a stronger weak acid, a stronger weak base. Otherwise, you'll do the wrong problem and get the wrong answer. So I want to review how you classify these substances. It sounds bad until you look at it all in one place like this. For strong acids, you know that it's a strong one if it's one of the 6. If it's not one of the 6, it's a weak one. And all of the weak ones you'll find in table 2. Sulfuric is strong, like we said, but the second step is weak. A strong base has to have OH in the compound. And the only thing OH can combine with is a positive, so it's going to be a metal plus OH. If you want to ask where weak bases are, the specific definition for a weak base is something that takes an H off of water to produce OH when you dissolve it. But if you want to remember it from a practical point of view, I would rather have you remember it like I'm going to show you. If you can remember that a weak base is anything on the right of the arrows in the Ka table, that's going to be, you'll be in good shape. And I want to show that also at the bottom of this page. I told you that the only base that's really considered strong in water is OH. There are a lot of bases that are stronger than OH, especially in organic chemistry. But if you put one of those in water, all the base does is pull an H off of the water immediately and produce OH. That's what's called the leveling effect of water. Any base that's stronger than OH is automatically going to produce OH. So all of the bases look like they're equal strength. I just want to practice a few of these classifying, and they're not difficult, but I want to go over it. If you wanted to classify HBr as a stronger weak acid, stronger weak base, you know that HBr is one of the 6. So it's a strong acid. If you look at the next one, HBrO, the O messes it up. So HBrO is not a strong one. It's going to be weak. And you can verify that it's weak because it is in the Ka table. The last two are the ones I really want you to make a mental note of because they're easy to forget. NH3 is the one that's on the right of the arrows, which makes it a weak base. NH4 plus is the one that's a weak acid. Those are really important to remember, especially when we do buffers. So here they are, and if you look at the Ka table, they're in the same row. And here they are circled. Cn minus is certainly a weak base because it's on the right of the arrows in the Ka table, and so is CO32 minus. It's a negative ion that comes from a diprotic acid. So here's the base, Cn minus. And here's the CO32 minus on the right of the diprotic acid arrows. Sodium hydroxide is a metal ion plus OH, which makes, and sodium makes everything soluble. So it's a soluble, strong base. HNO2 is not one of the 6 strong ones, and so it's a weak one. It's also in your table. And here it is circled. HF is not one of the 6 strong acids. It is a weak one. And here it is circled. The last one, oxalic acid, is a weak acid because it's not one of the 6, and it's also a diprotic acid, so you find it on page 10, the back of the Ka table. And there's oxalic acid on the left. Before we actually get into calculating the pH of a weak base, I want to demonstrate to you that calculating the pH for ammonium, which is a weak acid, is absolutely no different than any of the problems we've already done with weak acids. We've already done acetic acid and carbonic acid. So I want to calculate the pH and percent ionization of 0.1 molar ammonium. So there's ammonium on the left, and you can also look up the Ka, 5.6 times 10 to the minus 10. If you make the ice table, it looks exactly the same as the others. It's got the 0.1 and 0, 0. The plus and minus x's are the same, and so you're going to end up with the same equation. You ignore the x and solve, and then you get the H plus, which is x, and minus the log is the pH. And if you want the percent ionization, you do the same thing. You take x divided by the original times 100. And that is a very small percent, but that's the way ammonium is. It does make solutions acidic, but it's a pretty weak acid. Now we just calculated the pH of ammonium, but I want to calculate the pH of the base ammonia. And that's going to be a different problem because if you put ammonium in water, it's an acid, but if you put ammonia in water, it's a base. And here's ammonia on the right of the arrows, so it's a base. I keep emphasizing this because people have such a great tendency to forget this. So we now want to calculate the weak base ammonia. So we're going to calculate the pH and percent ionization of 0.05 molar ammonia. You already know it's a base, and so the pH has to come out above 7. This is how you can check. You can think about it in your head. You know you got to get greater than 7. The number that's listed as the Ka is the number for ammonium. So we have to use that to get the Kb for ammonia. When you put ammonia in water, it pulls an H off the water, gives you OH. So the ice table is going to look like this one. And when you do it, it looks just like the other one for the acid, except that water is present. You're not going to put anything underneath the water column because water is not in the equilibrium constant. So when you write the Kb for ammonia, you are going to write it as with the OH on the top, and you have to get a number to set this equal to. When you plug in the bottom row, the equilibrium row, and cancel the X, you get the same expression as you did for acids, but you can't set it equal to the Ka. So what you have to do is do the first step that's extra in a weak base problem is you have to do the 1 times 10 to the minus 14 divided by the Ka step. And I did that for the ammonia. Whenever I do these in either the worked out homework or in the lecture, I always put this calculation in one of those dashed boxes so you recognize it. And when you're doing a base problem, you have to set x squared over the original equal to the Kb. Once you do that, solving it is just like for an acid problem. You multiply both sides by the denominator and take the square root to get x, but this time x is not h plus. This time, since it's a base problem, the x is going to come out equal to OH. So that means since x is OH, you're going to have to do an additional step above the acid problem. Since the x equals OH like it did in a strong base problem, when you take minus the log, you actually get the POH, and so you also have to do the extra step of taking 14 minus at the end in order to get the pH. And if you want to get the percent ionization this time, you're still going to take x over the original times 100, but the x is OH this time. And if you look at that number, 1.9%, that's what we expected, because when we first started this, I told you that the reaction occurs about 2%. 1.9% is about 2%. Now this one is meant to be a little bit of a surprise because, like, what the heck is this stuff? But I want to calculate the pH and percent ionization of 0.25 molar. What is that? Well, let me say that I'm not going to give you one of these that's not in your table. So if you're not familiar with it, you just have to go to the Ka table and see if we can find it. Since IO minus is on the right of the arrows, you can tell that it is a weak base. So we're going to calculate the pH of a weak base. As I said in the previous problem, that means then that the pH has to come out above 7. The ice table looks exactly like ammonia, except it's a different starting amount. And because it's a base, you know that you have to write a Kb, not a Ka. The equation is going to come out x squared divided by the original, just like always. But because the IO minus is a base, you can't use the Ka that's listed in the table directly. You have to do that calculation of 1 times 10 to the minus 14 divided by the Ka, and that's the Kb, which is what you set the equation equal to. And then you go through the whole solving process, and when you get to the end, the x you get is OH. So you're going to have to do the additional step also of taking 14 minus, and that gives you the pH. And then when you calculate the percent ionization, you're going to take the x you got divided by the original times 100. And that's a pretty large ionization, but it's 4.2%, which is less than 5%. And remember, even if it is greater than 5%, you can still ignore the x relative to the larger number. Before we leave this class, I want to show one more principle that we're going to use next time. And this is just not a math problem, but it is something that's a concept. If you look at the equation we derived for Ka of an acid times the Kb of the conjugate base, you know that that equals a constant, which means if you take two acids, one is stronger than the other, the larger the Ka goes, the Kb has to go down, which means the conjugate base will be weaker. And the reverse is also true. If the weaker of the two acids is going to have the stronger conjugate base. I want to show you that with an example that you don't even have to have numbers for. You can do it in your head. Look first at the HCl, which splits apart 100% into ions. Cl- is officially called the conjugate base of HCl, but in water, Cl- is so weak that it doesn't even act as a base, because the HCl is always 100% ions, and Cl- has no ability to act like a base, which means it can't take back the H plus because it always stays separate from it. So it is such a weak base that Cl- doesn't even act like a base in water. But if you look at the weak acid HF, the F minus, that's the conjugate base that it produces, has a good amount of tendency to accept the H plus back. As a matter of fact, when you put those together in water, 95% of the HF is going to stay together as molecules because the F minus is a relatively stronger base. So when you do this, you're seeing that as the acid gets weaker, the strength of the conjugate base is getting stronger. I made a table of these because I wanted to show you how this works with real acids. The strong acids that I wrote above this, at the top of this table, you could put all 6 of them there. Actually, I only used 3 of them as representatives. And if you look at the conjugate bases on the other side, all of the strong acids have conjugate bases that are so weak that they don't even act as a base in water. You have to put those into an organic solvent before you see the fact that they can act as bases, but not in water. And the thing I also want to say is that all of the strong acids look equally strong in water, because 100% is 100%. But if you do those acid strengths in an organic solvent, you would find out, for example, that HClO4 is a much stronger acid than HCl, but in water you don't see it because they're both 100%. That's what's called the leveling effect of water. All acids that are stronger than H3O plus look like they're equal because they're all 100%. If you go on that table now, you can see that when you decrease the strength of the acid, the strength of the conjugate base increases. By the time you get to carbonate and phosphate, you're getting closer to OH, and I said that OH is the strongest base you can have in water. I showed you a couple of bases there that are stronger than OH, but if you put those in water, all that's going to happen is they're going to pull an H off the water, and you're going to get OH. That's a leveling effect also. All the bases stronger than OH look equal because they're going to pull an H off of water, and all you're going to get is OH. Now, this is we're going to use in the next class because we're going to talk a lot about the negative ions that come from strong acids especially, but I'm also going to use the table in general. So next class, we're going to look at the pH of a substance that we did not do today. The substance that we did not do is diprotic. The substance that we did not do today is the pH of salts. And so that is what we're going to try to cover next time. Now, though, you have everything you need to study for the first exam because it only covers homeworks 1 to 3. The next lecture will be the first one on the second exam.